Hi, welcome to Unacademy. Unacademy is the India's largest online learning platform. So we are happy to announce that now Unacademy is going to handling GATE and engineering service syllabus. So they gathered best faculty from the throughout the India. They are assisting the students with this faculty. Okay. Now, just first I am introducing about myself. I G Venkata. I have 16 plus years of teaching experience. So far, I mentored more than 60,000 students for their GATE examinations. At present, I am pursuing PhD from JNTU Kakinada, and my specialization is VLSI design. First, we check how to get the Unacademy learning app into our device. Just go to Play Store, type Unacademy. Just type Unacademy. Then you get the Unacademy learning app with this emblem. Okay, so now just go to this install button, click on this install button. Just click on this install button. It will install the Unacademy learning app into your device. Unacademy learning app into your device. Okay. Once you open the Unacademy learning app, in that you observe what are the different courses we have in that. Different courses in that, and each course handled by how many, who are the faculty handling the subjects in that respective course. For example, I am taking computer science. In computer science, who are the top educators handling these subjects? In electronics and communication engineering. In electronics and communication engineering, what are the different subjects we have, and each subject handled by which faculty? You get that information. And if you want brief information about faculty, there you get that brief introductory about that faculty also. Okay. Now, here we check some of the top faculty from Unacademy. Tiwari, he is the IIT topper. Ankit Goyal, he is the All India top rank twice in GATE. Okay, and he got the President's India Gold Medal in IIT Indore. Okay, now Jaspal Singh sir, he is the ex-IAS officer, and Jain sir, he is the top science CSE faculty. Now here are few of the top faculty from different disciplines. Now we are happy to announce that we are going to start new batches for GATE 2022 and 2023 for in different disciplines. In mechanical engineering, we started two batches, one for GATE 2022, other one is for GATE 2023. There is a ascend batch for GATE 2023. There is a ascend batch for GATE 2023. This batch started from 8th February 2021. And there is a eval batch for GATE 2022. This is for mechanical engineering. Here you can observe different faculty who are handling the courses, different subjects in that mechanical engineering. This batch started from 8th February 2021. Next, there is a ascend batch for GATE 2023. Ascend batch for GATE 2023. This is for civil engineering. This batch started from 8th February 2021. And don't forget to use my code VRAW10 during subscription. By using this code during subscription, you get 10% of discount. You get 10% discount by using this code during subscription. Next, there is a eval batch for GATE 2022. This is for civil engineering. Okay, civil engineering, and this batch started from 8th February 2021. Next, again there is a eval batch for GATE 2022. This is for computer science and information technology, CSE department. Here are the top faculty you can observe for CSE department. Okay, now this batch started from 8th February 2021. And there is a ascend batch for GATE 2023 for electrical engineering. So these are the top faculty you can observe for electrical engineering. This batch started from 1st February 2021. Next, there is a Ascend batch for GATE 2023. This is for Electronics and Communication Engineering. Here are the top faculty who are handling the subjects that. Now this batch started from 1st to February 2021. And there is a Evolve batch for GATE 2022. This time this is for Electrical Engineering. This batch started from 1st to February 2021. Next, there is a Evolve batch for GATE 2022. This batch started from 1st to February 2021. This is for Electronics and Communication Engineering. Next, there is a Evolve batch for GATE 2022 for Chemical Engineering. This batch started from 25th January 2021. Okay, if any of your friends are in chemical engineering, please inform this one to them. Okay, chemical engineering GATE training is available in Unacademy, because at outside it is not possible, very rare condition, only 1% of chance getting the training for this chemical engineering. Okay, so you must thank to Unacademy for this reason. They gathered top faculty who are available for that respective discipline. They gathered all the faculty and they are providing support to the students who required GATE training for chemical engineering. Okay, don't forget to use my code VRAW10 during subscription to get 10% discount. Okay, now so these are the different disciplines available in Unacademy for GATE and engineering service: mechanical engineering, electrical engineering, civil engineering, computer science and IT department, instrumentation engineering, production in the industrial, chemical engineering, and electronics and communication engineering. These are the different engineering disciplines available in Unacademy for GATE and engineering service examinations. Next, here there are two types of subscriptions. First one is the plus subscription. This is the basic plan. Second one is iconic subscription. This is the next level of the basic plan. In this, we provide a personal coach to the student. Okay, so India's best educators are going to handle the classes here. There are interactive live sessions, structured courses and PDFs they will provide, and live tests and quizzes. This is the most important thing here. In this fourth aspect, we will show the difference between the plus subscriber and iconic subscriber. Okay, so you have to write the exam and you have to analyze with your own here. But here, once you've written some text, the test is going to be analyzed by personal coach who are allotted to you. Okay, he will analyze that personal test and they will prepare a study planner for that, and they will provide that study planner to you. Based on that study planner, you can continue your preparation. In that study planner, they prepare the study planner based on where you are strong, where you are doing mistakes, where you need much preparation, in which topic, in which subject, in which topic, which area. They will prepare all those things. Okay, based on that they will prepare a study planner and they provide material also to you. By following these two properly, definitely a student will get success in their examinations. Okay, so my dear students, don't waste your time. Whatever thing is happened at outside, your learning process should continue. Okay, so join these plans. Now just if you observe the cost of each and every plan, they are just a nominal amount. So if you check the plus plan, okay, the cost of the plus plan is, see here are different subscriptions: 1 month subscription, 3 month subscription, 6 month subscription, 1 year subscription, 18 months, 24 month subscription, like that. For 1 year subscription, it is a cost of 27,225 rupees. 27,225 rupees. Okay, that is the cost of 1 month subscription. Okay, now After using my code VROUT10 during subscription, you get 10% discount. After discount, this is the cost. And if you compare this cost with the travel expenditure, what is taking through to travel from your home or from your college to the location where you are taking the training, okay, and outside, the traveling cost for throughout the year is more or less equal to that amount. Hardly 1 or 2,000 variation, not much, I think so. Okay. Even if you take the auto for a 3 kilometers or 4 kilometers, you have to pay minimum 100 rupees for that. Okay. In this situation, the cost of, for throughout year you need to travel. For that, the expenditure is more or less that one. So just by sitting at your home, by spending travel amount, whatever the amount you are spending for throughout the year, by spending that, you get whatever the benefits you are getting there, that benefits you can get here by sitting at your home itself. Okay, everything will come in front of your screen. So next plan is iconic plan. In iconic plan, only two subscriptions, 12 months plan and 24 months plan. Okay, in 12 months plan, you have to pay 50,250. By using my code VROUT10 during subscription, you get it with 10% discount, that is 45,225 rupees. 45,225 rupees. Okay, so you have to pay here only 45,225 rupees. Okay, now this is the case in 24 months, 74,000. After discount, it is 66,600. Okay, for third year students, this is the suggestible, and final year students, this is the suggestible one. Here we provide a personal coach. He will take care of complete your examinations and what you have to prepare. Okay, where you are strong, where you are weak, where you need much preparation. Okay, where you are doing mistakes. Even though you prepared well, sometimes, so most of the students are committing mistakes. Okay, with that mistakes only, they are losing nearly 10 marks. Okay, if you gain that 10 marks, our intention to provide that plus educate excess person to you is, as a coach to personal coach, is to gain that 10 marks. Whatever the 10 marks, 10 plus marks nearly they are losing, 10 plus marks, whatever the marks they are losing, we need to gain that marks. By gain that marks, if you are getting 60 marks, if you are losing 10 marks in that, now your marks is only 50. Your rank is close to 3,000, 4,000 rank. Okay, if we gain that marks of 10, okay, if you get that marks of 60, okay, if we protect the 10 marks, now your marks is 60, then your rank is below 700, 800 like that, or 500. Once your rank is below 1,000, there are much more chances to get the admission in IICs, IIT and IIC. Okay, IIT and IISc. Okay, and there is a chance of, if you have in so much amount of reservation, then there is a chance of getting central government job also. So my dear students, don't waste your time. Okay, enroll today and don't stop your learning process. Don't forget to use my code VROUT10 during subscription to get 10% of discount. Okay, thank you. Thanks for spending your time with us. Now we are moving to our topic. Now our topic is VI characteristics of PN junction diode. See, just so far we completed PN junction diode reverse bias and PN junction diode forward bias. Okay, and in forward bias, whatever the diode current equation we have, we completed that one also. Okay, now I'm moving to VI characteristics of PN junction diode and the effect of temperature on this VI characteristics. Okay, now, so first I'm writing the VI characteristics. VI characteristics of diode. VI characteristics of diode. Yeah. Now we know the VI plot, already we studied that. And this is the diode current and this is the diode voltage. Now the plot is like this. Like this. So there is an exponential increment in diode current. Exponential increment in diode current. Okay, like this you can define your PN-Junction diode. Now there is a voltage, we called it as a V gamma cut-in voltage. There is a rated current, that means a maximum current is the rated current of the diode. If the current is more than that, your diode will damage. Okay, so 1% of that rated current, here 1% of that rated current, 1% of that rated current, here you get. Now at this point, whatever the voltage you are applying to across your diode, that is called cut-in voltage. So now you can define, now this you called it as V gamma is cut-in voltage. So this is the minimum voltage you need to apply. Cut-in voltage or threshold voltage. Threshold voltage, or you need to apply minimum volt this much voltage, and it sometimes it called as knee voltage. Knee voltage. Knee voltage. Okay, so this is the minimum voltage you need to apply to get your diode into conduction. Okay, now under reverse bias conditions, this is the applied reverse voltage, this is the reverse current. Initially you get some current, increment in current little bit, and after that that current is constant. Okay, and once it reaches the voltage increasing, so that current is more or less constant, but once it reaches the breakdown voltage, now breakdown takes place, breaking of covalent bonds. This is the breakdown voltage, and this is the current I0 what you are maintaining reverse bias, constant current. We called it as reverse saturation current. So two important parameters we introduce in VI characteristics of PN-Junction diode. The first one is V gamma cut-in voltage or threshold voltage or knee voltage. Second one is I0 reverse saturation current. I0 is called reverse saturation current. Reverse saturation current. Okay, from this plot student can understand what you are going to be understanding from this. And one more important thing, don't forget the current in this in forward bias is of the order of milliamperes. Voltage reverse current of the order of microamperes or nanoamperes. In case of germanium it is microamperes, in case of silicon it is nanoamperes, and it is of the order of volts, forward voltage, and reverse voltage also of the order of volts we are increasing. Okay, if you want to define, now I am concentrating on forward bias. This is our forward biasing condition, forward bias. In forward bias, ID equals to approximately 0 for applied diode voltage is less than V gamma. If applied voltage is less than V gamma, diode current is approximately 0. Okay, and which is equals to I naught into e power Vd by eta Vt. This is the case for if applied voltage Vd is greater than V gamma. That is the diode current equation. This is the case for its ID. Okay, and the current ID is of the order of milliamps. Okay, sorry, here -1. This is the approximate value. Exact value is -1. Okay, now from this, what I want to get as a student, what I learn from this? See, the basic application of PN junction diode is as a switch. That is the basic application. Okay, if you take a switch, it has two conditions. It has two modes of operations. One is on, other one is off. First mode of switch operation is on switch. Second one is off switch. Second mode is off. In on mode, it should behave like the short circuit. On switch. Off switch means it is open circuit. This is the off switch. Okay, now we need to check is this diode is operating as a switch or not. If it is operating as a switch, in which region it acts as a on switch and in which region it acts as a off switch. Now, based on this plot, how can we understand? From that plot, we are going to calculate the amount of resistance it offers in that biasing region. If resistance is low value, then we can say the diode is operating as a on switch in that region, and if resistance is high value, then we can say the diode is acting as a off switch in that respective region. Okay, now how to get that values? Now first I am going to taking in, and one more, here we have two types of resistances. Now I am going to next. Here we have two types of resistances: dynamic resistance, static resistance, and dynamic resistance. Here we have two types of resistances. Types of resistances in PN junction. So from PN junction you can get these two resistances. One is the static resistance. And the second one is the dynamic resistance. Static resistance and dynamic resistance. What is this static resistance and what is this dynamic resistance? Now we check it. So for better understanding purpose, I am going to taking its VI plot. First I am taking static resistance. Just go to it's a VI plot. And it is ID of the order of milliamperes, and it is Vd of the order of volts. So this is the plot we have in forward bias. And somewhere here we get cut-in voltage V gamma. Okay, now static resistance means just take a point, any point on the plot, any point as you wish, some point on this plot, just extend that point onto the current plot y-axis and voltage plot x-axis. Now take that voltage by current. Voltage by current. That means inverse of the slope of that. Now that static resistance, for example, at this point I want to get. Now let us, I am assuming at this point, okay, diode current is okay, let us, I am taking 10 milliamps, and the applied voltage is let us 1.5 milliamps, 5 volts, let us 1.5, okay, let's take 2 volts, because 10 milli you taken, so you can apply 2 volts minimum, no problem. 2 volts I applied, okay, 5 volts, okay, whatever it is, it's not an issue. So 5 volts for easy simplification. Now this is the points. Now static resistance in forward bias is, now in forward bias, first one is in forward bias, that static resistance is VD by ID, simple, VD by ID. So VD is 5 volts by ID is 10 milliamps. So now by just simplify this, it is 1 and it is 2 milli. So it is 1 by 2.5 milli, 10 power 3. So it is a 500 ohms. So it is giving the resistance of the order of 500 ohms. Okay. Now, so the resistance in this region is of the order of ohms, Okay. Now, in reverse bias we check it, the same thing. Just I am completing that reverse plot also. So this is the reverse plot. This is of the order of microamperes, IR. This is applied reverse voltage, and we call it as I naught. Okay, second case in reverse bias, same, we are reverse voltage by IR, reverse current. So reverse voltage by reverse. Now let us take it as a 2 microamps. Now the applied voltage is whatever the voltage you can apply, the same thing you are getting. Let us, I am taking voltage 2 volts, minus 2 volts, reverse voltage. Now it is a 2 volts by IR is 2 micro. So that is 1 into 10 power 6 ohms. That means 1 mega ohm. That is the amount of resistance. Okay. Now compared to 1 mega ohm, this is more than, this is very low value. So 1 mega ohm is much greater than 500 ohms. Okay. It means in this region, reverse bias, because of high resistance, you can set your diode is operating in as a open switch. And similarly in forward bias, you can set your diode is operating as a on switch. Okay, is it okay, sir? That is the on switch. Now this is about static resistance. In forward bias we taken, and in reverse bias also we taken that static resistance, and from the calculation of that we observed it is in forward bias it exhibits low resistance. So once it exhibited low resistance, we can set it as acting as a on switch in forward bias, and in reverse bias it exhibited high resistance, so it acts as a open switch. Okay, this is the static resistance. Next we are going to take the dynamic resistance. So the next topic is dynamic resistance. Okay, for better understanding purpose, once again I am taking the plot. VI plot. As a student, you should be in a position to draw this VI plot whenever you required. Okay, don't forget. Now this is a ID of the order of milliamps, VD of the order of volts, reverse current IR of the order of microamps, reverse voltage VR of the order of volts itself. Now this is the plot in reverse bias. So in forward bias, this is the plot. Somewhere here V gamma. Now we are going to dynamic resistance. See, in dynamic resistance in forward bias, see, dynamic in this sense, dynamic resistance is nothing but a dV by di, change in voltage by change in current, change in voltage by change in current. Let us, I am taking 2 points on this plot. Previously we taken only 1 point. Now I am taking 2 points, somewhere here and somewhere here. Okay, just extending those 2 points on voltage axis. Similarly, I am going to extending those 2 points on current axis. Do the same thing here also on voltage axis, on current axis. So in current axis you get the same value. Now this is 2 micro amps. Previously what we taken, it is a 1 volt, it is 2 volts. Let us, now I am taking this is a 10 milli and it is going to be the 5 milliamps, 10 milliamps it is. Now it is 5 volts and it is 3 volts. Okay, now here it became delta V, that is 5 minus 3, which is 2 volts, and it became delta ID, delta I in forward bias. It is 10 milli minus 5 milli, 10 milli minus 5 milli, that is 5 milliamps, that is the delta I. Now in forward bias, dynamic resistance is delta V by delta I, that is, so dynamic resistance we represented by RD. Now its value is delta V is 2 volts we got by 5 milli, 2 by 5 milli. Okay, so it is 4 by 10, so it is 0.4k, so it means it is 400 ohms approximately. So its value is 400 ohms. Okay, now we check the same in reverse bias. In reverse bias, here delta V is 1 volt, delta V is 1 volt, 2 minus 1 1 volt, but delta IR or delta I is 2 micro, because I naught is constant. This is I naught is constant, so 0. Now delta V by delta I is 1 by 0 in infinity. So ideally in infinity we get, practically we get of the order of mega ohms. It is ideal value, ideally, practically of the order of mega ohms. Okay, of the order of mega ohms practically. So mega ohms of resistance is very high value compared to 400 ohms. Okay, so it behaves like an on switch again in forward bias because of low resistance. Because of low resistance it behaves like on switch, and because of ohms, mega ohms of resistance, here it behaves like off switch. Okay, so like this we can take the dynamic and static resistances. Okay, and we have different diode modelings, small signal modeling, ideal modeling, constant voltage drop model, piecewise linear model, exponential model, like this. Okay, later in problem sessions, by taking a problem, we can solve that problem effectively by applying that model. Okay, now this is about different resistances calculation from the VI plot of a PN junction diode. And from the knowledge of that resistance, you can say in forward bias, approximate amount of resistance it offered, it is of the order of ohms, and in reverse bias, the amount of resistance it offered is of the order of mega ohms. So based on this mega ohms, ohms is very less value, very small value, negligible value. So in forward bias, PN junction diode acts as a on switch, and in reverse bias, PN junction diode acts as a off switch. We concluded that. Okay, now in VI plot, here we defined two important parameters. First one is the I naught, the reverse saturation current. Second one is the V gamma, cut-in voltage. These two parameters are temperature sensitive. Once temperature is changing, these two parameters are going to change. Now we just check that how that values are changing. Now it is effect of temperature on VI characteristics. Effect of temperature on VI characteristics. First I am taking the forward bias. So this is the plot in forward bias. Forward current and reverse forward voltage. So diode voltage in general we are taking, and ID we are taking here of the order of milliamps. It is of the order of volts, and this is our plot. Yeah, somewhere here we have cut-in voltage V gamma. So cut-in voltage we represented here in this sense. At this cut-in voltage, what happened is, whatever the depletion region width we have under open circuit condition, it is nullified, approximately 0, and a considerable amount of charge carriers crossing the junction. Okay, if I am going to increasing temperature in PN junction diode, what happens? Just see this. This is the case here. So here we have a depletion region. Don't forget, under open circuit condition we have a depletion region. This is the depletion region what we have. Okay, to nullify this depletion region, we brought up to this voltage we need to apply. Okay, after this voltage, charge carriers are moving freely. Now in this region we have plenty of covalent bonds. What I am doing is I am going to increasing the temperature. Once increasing the temperature, what happens is, whatever the covalent bonds present in this, those covalent bonds are going to start breaking, because thermally you are applying external energy to that. Okay, once covalent bonds are starts breaking, electron hole pair is generating. Okay, now once charge carriers are generating, initially we call it as a depletion region. Why it is depletion region? Because of it is a depleted of charge carriers. That means there is no charge carrier in that. But now charge carriers are introduced in that due to increase in temperature. So once charge carriers are present in that, then after then you can't say that is a depletion region. So that means simply whatever the depletion region we have, there is a chance of decreasing the depletion region, or more charge carriers are available. Previously there is no charge carrier in this region. See, initially no charge carrier here. There is no charge carrier here, no free charge carrier, only depletion region you have. Okay, let us take the case now with temperature. So with increase in temperature, so this is the case. Now just we increase the temperature here. So increase the temperature. Once we increase the temperature, what happens? Here covalent bonds are breaking, electron hole pairs are generated. Okay, here new charge carriers are generated. That means you are spending this much amount of voltage to bring the charge carrier from here to here and here to here. But here no need of bringing new charge carrier. Already few charge carriers are available in that. Okay, already available in that. Now the amount of voltage you need to spend only for taking these charge carriers from here and moving cross the junction. Take this electron, cross the junction. For that reason only, that purpose only, you need to spend the voltage. Okay, so instead of applying this much voltage, less than that voltage is sufficient. Now the plot is like this. Your plot is like this. Okay, this is the plot. Now V gamma is decreased. This is the new V gamma. Okay, so V gamma value is decreasing. So by increasing temperature, cut-in voltage is going to be decreased. That is the final statement. Therefore, by increasing temperature, the cut-in voltage V gamma decreases. Okay, from practical values, from experimental results, they calculated that the decrement is minus 2.5 millivolts per 1 degree centigrade rise in temperature. This is the dV gamma by dt. So this negative represents decrease in V gamma cut-in voltage, that is amount of 1.5 millivolts per 1 degree centigrade rise in temperature. Okay, so this is the variation in cut-in voltage by increasing temperature, or effect of temperature on cut-in voltage V gamma. So for every 1 degree centigrade rise in temperature, V gamma is decreased by 2.5 millivolts. And one more thing, this V gamma value is approximately 0.2 volts for germanium and 0.7 volts for silicon. If you observe this, practically default diode what we are using is germanium, sorry, silicon. This is the practical default diode what we are using, silicon. If you observe this one, see, V gamma is 0.7 volts for silicon. So this is 700 millivolts. You can write this one also, 700 millivolts. Okay, for example, 5 degrees centigrade of temperature is increased. So 5 degrees centigrade increment in temperature is not that much easy. Okay, so what's 5 degrees centigrade increase? For 5 degrees centigrade increment, 5 degrees centigrade. Okay, let us take 10 degrees centigrade for easy calculation. For 10 degrees centigrade increment in temperature, change in V gamma is minus 2.5 into 10, because for every 1 degree centigrade 2.5 milli, so it is milli. Now it is minus 25 millivolts. Now after increasing temperature, now the new value is 700 millivolts minus 25 millivolts, which is 675 millivolts, which is 0.675 millivolts. So during the calculations, okay, whatever the values here we are handling practically. So 0.7 volts, 0.76, 0.675 volts not shows much variation in the calculations. Not shows much variations in the calculations, because that too we are taking e power Vd. Okay, e power we are taking applied voltage. Okay, so that's why the effect of, there is effect of temperature on V gamma. Okay, no doubt at all, but it doesn't pose much effect, not considerable amount of effect on the V gamma. Okay, that is the conclusion. So next I am going to effect of temperature on I naught. This is the important parameter, because I naught seems to be very small, but the effect of that I naught is not that much easy. Okay, I naught, effect of temperature on I naught, reverse saturation current or in reverse bias. In reverse bias. So for my easy understanding purpose, just I am taking the plot in reverse bias. So only I am taking reverse bias plot. So this is a VR, applied reverse voltage. This is the applied reverse current. Because it is more or less constant, that's why I am taking small. It is reverse current of the order of microamps. Now your plot is like this. This is the reverse saturation current I naught. Reverse saturation current I naught. So I naught is of the order of microamperes. Of the order of microamperes. We know that. Now in reverse bias, we are getting the small current. Why it is? Why? Because there are very few number of minority charge carriers. So once minority charge carriers are cross the junction, there we get the current. See this. Now this is the under open circuit condition, the PN-Junction diode. Okay, and under open circuit condition, this is the depletion region with, under open circuit condition, this one. Okay, open circuit condition. Now once it is in reverse bias, what happens? Depletion region width is increasing. This is under reverse bias. In reverse bias, so this total thing is the depletion region. In depletion region, we have only immobile ions and plenty of covalent bonds between silicon atoms. Okay, now once we increase the temperature, and one more, here we are getting I naught because of this is connected to this is P region and N region. We connected P region to negative and N region to positive. So whatever the electrons minority charge carriers we have, and whatever the holes minority carriers in N region are repelled by this. That means these movement of charge carriers is due to the electric field. Now these electrons are moving this side and these holes are moving this side. Due to this charge carrier movement, we get I naught. Okay, fine. Now once temperature is increasing, in this region, whatever the covalent bonds present in this, that covalent bonds are breaking in the depletion region. So covalent bonds are breaking. So here covalent bonds are break. Covalent bonds are breaking in depletion region. in depletion region. So once covalent bonds are breaking, new electron hole pairs are generated. So in this region now I have a plenty of, that means more number covalent in this depletion region. Now I have, once temperature increase, new electron hole pairs are generated. This is the hole and electron, hole and electron, hole and electron, hole and electron. Okay, now due to this applied reverse voltage, this negative, the electrons which are available here are going to be, these electrons are moving this side and these holes are moving this side. So in early case, only the electrons which are in p region are going to be crossing, but now new charge carriers are generated at the junction. Now these charge carriers are crossing the junction. That's why more amount of charge carriers are crossing the junction per second. Now I naught value is increasing. Therefore, by increasing temperature, I naught value increases. Okay, I naught is increasing. Now how much amount it is going to be increasing is, for every 1 degree centigrade rise in temperature, see this, for 1 degree centigrade increment in temperature, I naught increased by 7%. For every 1 degree centigrade rise in temperature, I naught increased by 7%. And for 10 degree centigrade rise, for 10 degree centigrade increment, I naught increased by double. Okay. Now you may ask one thing, sir, for example, temperature is increased only 2 degrees centigrade, 5 degrees centigrade, 12 degrees centigrade, then what is the value of I naught? How can we calculate? So there is a equation for that. That is, let us take at temperature T1, I naught value is I naught 1, and at temperature T2, I naught value is I naught 2. Now we can relate these two is I naught 2 equals to I naught 1 into 2 power T2 minus T1 by 10. By using this equation, you can calculate the value of increment or change in reverse saturation current I naught. Okay. So this equation is important, sir. Now, sir, I naught seems to be very small, but the effects of this one is very high. Okay. So saturation current, simply for your better understanding, I naught leakage current. Okay. Now, you know what is the effect of how much it disturbs leakage current in our life. We are expecting free flow of water. Once tap is closed, we are expecting no movement of water, not even single drop we are expecting from out of it. For example, so drop by drop water is coming out into that. Okay, during daytime it's not much effect, but in night time when I'm going to sleep, okay, then by drop water is coming out. Now that is the that creates very disturbance to me, and one more, water tank is full, one by one water drop is coming out, it's okay. If that leakage is up to 1 hour 2 hours, hardly it is going to be a one bucket, that means a 20 liters or 25 liters of water. If that leakage is for a 1 month, you can imagine that how much water you are going to be wasting. Okay, so don't take light when there is a leakage. Okay, as early as possible that leakage should be blocked. But nothing is ideal in the universe. Because of that, we are getting the some leakage current in the diode. Because of this leakage current only, there is a in a transistor we have a thermal effect. So in a BJT, we are using heat sink. In your silicon, we are using heat sink. This is also one of the reason. In our transistor, there is a temperature effect. Due to temperature, I naught is increasing. Once I naught is increasing, that means IC naught, there we called it in transistor. Once IC naught is increasing, IC is also increasing, then more temperature is generating. So to cool that more temperature, we need to use a heat sink there. Okay, this is the effect of this. So this is the effect of temperature on VI characteristics of a PN junction diode. Okay, and one more. Sorry. So we derived already diode current equation. That part is completed. We've written ID is I naught into e power Vd by eta Vt minus 1. Okay. This is the exponential way of representing the diode current. That means I am going to representing my diode plot, Vi plot, like this. This is the Vi plot. This is the exponential one. Okay, and sometimes you can write the diode current equation is approximately I naught into e power Vd by eta Vt. And we can write a diode current equation Vd is from this eta Vt into ln of Id by I naught. So sometimes you get a problem. How much amount of voltage has to be applied to a diode? To get a diode current is 1000 times more than reverse saturation current. Okay, so then such type of cases you need to apply this. Okay, now I am doing a problem on this. So how much amount of voltage is applied to get a ID 1000 times more than I naught. So in that case, I am taking silicon diode, so germanium diode. For germanium diode, eta is 1, Vt is 25 millivolts, that means 0.025 into ln of 1000 means it is 1000 times I naught. ID is by I naught. Sorry, this is I naught. 1000 times. ID became 1000 times. Now it became, see, I naught gets cancelled. ln of 1000, 10 power 3, take 3 this side, 3 into ln of 3, ln of 10 is 2.3, 2.3 into 3, 6.9. So 0.025 into 6.9 volts. This is the amount of voltage you need to apply, okay, to make the diode current 1000 times more than the reverse saturation current. Okay, like that you can solve. This is the exponential way of representing the diode. Exponential way. Exponential representation of the diode. For our easy understanding purpose and for our easy processing purpose, sometimes we go and define our diode in different formats. See this. Here it is current and voltage in forward bias. Reverse bias is common. Now the second one is, sometimes we define our diode like this. Like this. This is, we call it as V gamma. Okay, this is, and another way of representing our diode is, this is V and this is I. Now the plot is like this. This is the plot. So here it is V gamma. Another way is, this is I, this is V. This is the plot. This is the plot. Here it is V gamma. This is V gamma. This is V gamma. After that, this is 0. This is V gamma. So this is exponential modeling representation. Exponentially you define your diode. Okay, and this is called piecewise linear model. Piecewise linear model. Okay, and this is constant voltage drop model. Constant voltage drop model. This is ideal diode. Ideal diode or ideal model. You can define in this region your diode by an equivalent circuit of simple. Here equivalent circuit you can write when we have a diode like this, you can write its equivalent circuit in this region is just its cut-in voltage V gamma and its dynamic resistance RD. Dynamic forward resistance or dynamic resistance in forward bias is RD. This is its equivalent model, equivalent representation in piecewise linear model. In constant voltage drop model, once you have a diode like this, your diode is in forward bias. Now the equivalent circuit you can take it as this one, V gamma. Okay. In this is ideal drop mode, ideal diode. So when your diode is in forward bias, you can take it as simply short circuit. That's it. This is the way of modeling the diode, different models. Now you may ask one thing, sir, how can we identify which model they given? They may give the model in terms of equations, or in terms of plot. If they given in terms of plot, we know how to replace your diode. Okay. If they given in terms of equations, how to solve that. Okay, how to identify that. Okay, everything we observed in small signal modeling of diode, and there itself we go for different possible models, these models, and we solve one problem. There was one beautiful problem on this. It was given in a GATE, previous GATE, I think so it was in 2013. Okay, we solved that one. 4 options they given in that. 4 options are applicable to that one, but based on the statement VI plot what they given, VI characteristics of the diode, it will change. Okay, we go to that problem later. Okay, so today just we rewind back what we discussed today. So VI characteristics of PN-Junction diode, just we draw the VI characteristics in forward bias and reverse bias. In forward bias, current is of the order of milliamperes, voltage is VD is of the order of volts, and in reverse bias voltage of the order of volts and current is of the order of microamperes. Okay, and here in forward bias there is one important parameter we define, that is V gamma cut-in voltage. It is also called threshold voltage or knee voltage. It is the voltage, diode forward voltage at which 1% of rated current we get. 1% of rated current. Next, reverse saturation current, I0. This is the constant current flowing through the diode when it is in reverse bias. Okay, and you can call it as also a leakage current. Now, in forward bias and reverse bias, after completion of the plot, we need to go for how it is going to be useful or what we can understand from this. This is the diode current equation in forward bias. Okay, now here my intention is, what is the application of PN-Junction diode? Now we know that the basic application of PN junction diode is as a switch. So it can behave like either on switch or off switch based on the biasing. In forward bias it is on switch and reverse bias it is off switch. Now we go on show that. Okay, so in that process I am going to calculating two resistances from the VI plot. Okay, one is the static resistance, then second one is dynamic resistance. Static resistance is the point to point value we take just to take a point on the VI plot. Okay, at that point what is the voltage and what is the current. Similarly in reverse bias also, what is the voltage at that point and what is the current at that point. Okay, we are taking and we are substituting that values in a this one. Now that I am taking that V by I, VD by ID. So it is nothing but a inverse of slope of this plot, inverse of 1 by slope of this plot. Okay, now it is 5 by 10 milli. There I taken 5 and 10 milli. Now it is of the order of 500 ohms it given. Similarly, I am going to calculating the same resistance in reverse bias. Now it is, I got here it is 1 mega ohm. So 1 mega ohm is very high value compared to 500 ohms. So when at this point, if I considered my diode is open circuit, at this point it should be short circuit. Short circuit. That means here it behaves like a on switch and here it behaves like a off switch. Okay. So finally we concluded in forward bias diode behaves like as on switch and reverse bias it behaves like off switch. So next, similarly we taken the dynamic resistance. Now we taken 2 points on that plot instead of 1 point, taken 2 points. From that we get the delta V and delta I. Okay, both the points are substituted in this delta V by delta I. Now we got 400 ohms in forward bias, in reverse bias we got mega ohms. Ideally 0 we get, infinity we get. Ideally it is infinity, but practically of the order of mega ohms you get. So mega ohms is very high value compared to the ohms. So in reverse bias it acts as off switch and in forward bias it acts as a on switch. And after that, so finally two parameters we concluded on VI plot. One is V gamma, other one is I naught. I am not touching the breakdown. So there is a separate session for breakdown point. We have a GNR breakdown and avalanche breakdown. We discuss later about that. Now I want the effect of temperature on this VI plot. So on this VI plot means we have two parameters. In forward bias there is a parameter V gamma. In reverse bias there is a parameter I naught. Okay, so we observed without applying any temperature in V gamma is this much. V gamma, why we are taking this much value is because of by applying the forward voltage to this. Okay, this forward voltage is going to take this hole through this and electron through this. So this voltage has to travel this hole from here to here and similar electron from here to here. For that you need to apply this much voltage to cross the electron junction, across the junction. Now the case here is once increasing the temperature at junction, more number of charge carriers are generated. Now electron is instead of available this electron here, now hole here, now hole is available in depletion region itself. Now electron is instead of available, electron is available here also. Now to cross this one, less amount of voltage is sufficient. Okay, that's why V gamma is decreasing. Now the decrement is for every 1 degree centigrade, it is decreased by 2.5 millivolts per degree centigrade. Okay, for every millivolt, it is decreased by 2.5 millivolts. Okay, but in practically we are not giving much priority to that variation. Why? Because silicon diode we are going to be using practically. Ideal for V gamma cut-in voltage for a germanium diode is 0.2 volts and for silicon it is 0.7 volts. 0.7 means it is 700 millivolts. Okay, 700 millivolts it is. So for even for temperature is increasing 10 degrees centigrade, the change in V gamma is 25 millivolts. Now it is 0.675 millivolts. Instead of 0.7 you have to take 0.675. Okay, in practical values, practical calculations, 0.7, 0.675 not provide that much deviation or not that much variation in the values. Okay, that too we are taking e power exponential. Okay, so this is the variation in V gamma with respect to temperature. Next, we are going to take the effect of I naught. See, in I naught also same thing. Once temperature is increasing, whatever the depletion region we have, that is increasing. Depletion region once is increasing, temperature increasing, more amount of covalent bonds are breaking in the depletion region. So more amount of charge carriers are available. So more number of minority charge carriers cross the junction. Now more amount of I naught we get. So by increasing temperature I naught, increasing temperature I naught is increasing. Okay, and this value is from practical values, from experimental results. They concluded for every 1 degree centigrade rise in temperature, I naught is increased by 7%. I naught is increased by 7%. For every 10 degree centigrade rise in temperature, I naught is going to be doubled. Okay, now there is a standard formula to represent variation in I naught with respect to temperature. Let us at temperature T1 current is I naught 1 and at temperature T2 current is I naught 2. Now the relation is I naught 2 equals to I naught 1 into 2 power T2 minus T1 by 10. So this I naught is called a leakage current also. Okay, so by using this equation you can get at one temperature I naught is that much, at second temperature what is the I naught. So you get that from this equation. Okay, and this is the diode equation we defined. ID equals to I naught into e power Vd by eta Vt minus 1. Okay, and for easy purpose we are taking this one like this. This is the exponential representation. From this I am taking Vd is eta Vt into ln of Id by I naught. Now here my main intention is how many ways you can define your diode, how many ways you can model your diode. This is the exponential modeling of your diode. Okay, you represented that one by an equation, that is Id equals to I naught into e power Vd by eta Vt. Already you defined it. Now instead of taking the plot exponential like this, for my easy calculation I am going to be defining that by linear. Okay, linear like this. So here this is called piecewise linear model. Now in that case your diode equivalent circuit is represented by V gamma followed by dynamic resistance, forward dynamic resistance. And already we derived an equation for that forward dynamic resistance, that Rd is eta Vt by Id, diode forward current Id. Already we derived. And another one, just whatever we have V gamma, we have like this sum. I am going to be keeping that vertical. That is another model. We call it as constant voltage drop model. Now the equivalent diode can be replaced by this simply V gamma. And another one is ideal model. In ideal model, just whatever the ID we have, I am moving this ID this side. V gamma, I am moving that V gamma into this side. Now this is the plot result. Okay, now in this, your diode is simply short circuit when it is in forward bias. Okay, so that is called ideal model. So like this, you can your diode can be modeled in a different way. Okay, so and these are the equivalent circuits, equivalent way of representing your diode in different models. And your diode model is not only represented by plot, by using equation also you can represent that. About those things we discuss in later classes. Okay, thank you. Thanks for your spending your valuable time with us, sir. Don't forget to use my code VRAO10 during subscription, and please hit this bell symbol to get the notifications from our side. And please join our Telegram group to get the latest updates on our upcoming videos. And don't forget to subscribe, and please give your valuable comments on YouTube. So those are helpful to us to strengthen ourselves and to provide a better and quality information to the upcoming students. Okay, now and once again I am thanking to one and all, and welcome to Unacademy, India's largest online learning platform. Thank you very much. Thanks for spending your valuable time.